Is my screen visible? Somebody please
Yes, sir.
respond.
Yes, sir.
Okay. So you see, this was the problem which was covered in your theory class, right? So you can see this is a grid problem. So today we will be ending the last practical. So we have to conduct 6 practicals, and this is the 6th practical, and it is based on your grid. Okay. So let me first of all take the problem which is covered in the class. Then I'll give you one assignment kind of a thing. Okay. So this was a problem which is covered in the class. So especially in case of grid, you see the geometry of the grid is defined in X and Y plane. Okay. So if you see from the top, you will see a grid of X and Y. Okay. So the geometry is basically defined in X and Y plane. Whereas if you see the loading part, so loading is parallel to the Z axis. Okay. So if I talk about talk in terms of SAP, so you can say the direction of the loading is in the direction of the gravity. Okay. So this was the problem which was taken in the class, wherein you can see the modulus of elasticity of the members is given to you as 2.54 10 to the power 7 kilonewtons per meter square, and the G value, that is modulus of rigidity, is 8.8 into 10 to the power 6 kilonewtons per meter square. B value is 230, D value is 550 millimeters, and accordingly J can be calculated and I can be calculated. Okay. While defining the members, so this is your member number 1. Member number 1 is from joint number 1 to joint number 2, and this is your member number 2. It is from joint number 2 to joint number 3. Member 1 is subjected to UDL, and member 2 is subjected to concentrated load at the center. Okay. Now in SAP, what happens is you have to give input as modulus of elasticity, but this G value is not taken as input in the SAP. Okay. So in your theory class, you might have seen there is a relationship between E and G. Okay. So the relationship says we can calculate the value of mu. So the value of mu comes out to be E divided by 2G minus 1. Okay. So now in the problem, the value of E is known and value of G is known. So I can substitute the value of E as 2.54 10 to the power 7 and the value of G as 8.8 10 to the power 6. And accordingly, I have calculated the value of mu. Mu is nothing but your Poisson's ratio. So mu value comes out to be 0.44318. Why I have calculated this? Because I have to give mu as an input, and the value of G as an input is not possible in the SAP. Okay. So let us start modeling this particular problem. So like I said earlier, if you see from the top, you should see the X and Y plane. Okay. So if you see the X direction, in the X direction, the member 2 is there parallel to X axis and its length is 2.5 meters, and member 1 is parallel to Y axis and its length is 3 meters. Okay. So basically when we will go in X and Y plane, so let me start on the SAP. So I'm selecting this one. So I'll be looking at X and Y plane. So if I talk about X, I want to have a spacing of 2.5 meters along the X axis. Okay. So along the X axis, I want only one grid space. Okay. And the spacing should be 2.5. Okay. Then if you refer along the Y axis, there is only one grid point is required, and it is at a distance of 3 meters. Okay. So along the Y, I want only one grid space, and it is at a distance of 3 meters. Okay. So if you refer the Z axis, which is a vertical axis, I don't want any grid in the Z axis. So I'm keeping this as 0. Okay. And there is no point in giving spacing because there is no grid in the Z axis. Okay. So if I click on OK, so you will see there is a grid, and here in this plane you can see this is X axis and this is Y axis. So you can see along the X axis we have a distance of 2.5 meters, and along the Y axis we have a distance of now 3 meters. Okay. So here this is Y and here this is X. Okay. Till now we were working in X and Z plane. So this is the first time we will be working in X and Y plane. Okay. So now if you refer this problem, we have to give the material properties and other details. So let me save the file first. So Let me save this file as grid grid 1. Okay, then the first thing I need to define is the material. Okay, so I'm selecting the material, I'm selecting the concrete, and then I'm going to modify this concrete. So here you see I have already entered the value of elasticity, that is 2.54 into 10 to the power 7 kilonewtons per meter square. So here this is 2.54 10 to the power 7, and at the bottommost corner you will find the units are kilonewton and meter. Okay, at the same time there is a Poisson's ratio. So here I have calculated the Poisson's ratio as 0.44318. so here also I have written 0.44318. okay, so these two things you have to give as an input, that is the Poisson's ratio, and there is a modulus of elasticity. Okay, then I am saying okay. So this is how I have defined the, or I have changed the material properties of the concrete. Then I have to define the frame sections. Okay, so in the problem the frame sections are defined as 230 width and 550 depth. So here this FACT1, that is frame section 1, so the depth is 550, so 0.55 meters, and this is 0.23 is the width, and it is made up of concrete, not made up of steel. Okay, so this is the concrete. So I have defined the material sections also. So now the materials are defined, frame sections are defined. Now I have to change the self-weight criteria. So self-weight criteria, I'm making this as 0. I'm just going for change of load, so that this value is now 0, and then I'm saying okay. So let me save the file. So right now I have defined the materials, frame section, and the static load case. So now I have to draw the section. So if I want to draw the section along the y-axis or parallel to y-axis, I have to draw a 3-meter member, and then along the x I have to draw a 2.5 meter length member. So along the y, so this side is your y, you can see the y direction over here. So I'm just going for drawing the frame element. So from here to here, this is my member number 1, and from here to here, this is my member number 2. So let me save it once again. And then if I see the 3D view, so you can see this is the 3D view. So here in this case you can see this is the x direction, so this will be 2.5 meter length, and this is your y direction, so this will be your this will be 3 meter length. Okay, so this is very much similar to this view, only thing is the orientation is slightly changed. Okay, so this is how we have defined the members. So now let me define the material properties and the frame sections to the drawed member. So I'm selecting both the members. I'm going for assign, say frame and frame section. So the frame section which we have defined earlier, this frame section I'm assigning to both the members. So FACT1 is assigned to this member number 1 and to member number 2 also. Okay, now according to this one, we have a fixed support at node number 1 and at node number 3. So let me select node number 1 and let me select node number 3. I'm going for the supports, and then I'm selecting the fixed support, and then I'm saying okay. So as soon as I say okay, you will find this both the nodes has been assigned a support of fixed support. Okay, then coming to the loading part, this is the long member. So member number 1, 3 meter length, and it is subjected to loading of 15 kilonewton per meter. So this is that member. So this is 3 meter length member, and here I am going to apply a uniformly distributed load of how much? 15. Okay, now you see the direction of this force is in the direction of the gravity, and you always remember the gravity is defined in the negative z axis or parallel to negative z axis in the SAP. Okay, so once I say 15, let me check the values. Yes, it is 15 kilonewton per meter. So once I say okay, so you'll find the loading is applied in the direction of the gravity, that is in the minus z direction. Okay, and it is applied at the member number 1. Okay, then I am going to select this member now, this one. So on this member there is a concentrated load of 40 kilonewton is acting at the center. Okay, so we can go for the relevance load over here. So I'm selecting this, assign frame span loading. So let me delete the uniformly distributed load first, otherwise it will be applied on the same member. So now I have to apply a load at the center. So I'm going for absolute distance, or I can go for the relative distance. So let us go for relative distance. So I want to apply the load at 50% length. Okay, so 50% means at the center, that is at 0.5. So this is a relative distance, and the magnitude of load is 40 kilonewton. Okay, now this 40 kilonewton is in the direction of the gravity, you can see over here. Okay, so once I say okay, so you'll find the load is acting in the direction of the gravity. Okay, so this is how we have to define the loading in the grid problems. Okay, so now I have to go for analyze. So in the set options, now since this is a grid problem, you have to go for the space frame where ux, uy, uz, rx, ry, rz both are now available. Okay, so then saying okay. So let me save the file one more time, and then I'm saying run. So analyze and run. If my input is correct, the solution will be complete. So you can see the analysis is successfully done. Okay, so now if you want, you can see the animation over here. So let me start the animation. So you can see due to the influence of the loading, the frame is deflecting like this. Okay, now the most important part is the solution. So what I'm going to do is I'll go to the file and I'll go for print output tables. So while printing output tables, I'll put the reactions also. I want to see the reactions also, and then I'll go for the print into a file, and that file is in C, SAP and grid1.txt. Okay, so let us open that particular file. So I'm going to see SAP and grid1.txt. Okay, so this is how our output file is now created. So now if you refer your problem, so this was a problem, the solution was also covered in the class. So if you refer the solution, what you will see, there are three unknowns, that is rotation about x, rotation about y, and the deformation about the z axis. Okay, so here you can see, let us talk about the deformation about the z axis. So deformation about the z axis, when you have done it calculation manually, so it was coming out to be minus 1.05 10 to the power minus 3. Okay, and here what we are getting is minus 1.148 into 10 to the power minus 3. Okay, so this is very close to each other. Okay, this value may differ due to the calculations, rounding of errors, and writing the numbers maybe up to 2 digits or 3 digits. So because of that, you may get some difference. But otherwise, if you see, this is 1.05 and this is 1.1, the direction is also matching and the power term is also matching over here. Okay, secondly, if you see the rotation about the x-axis, that is r1, so this is theta x. So theta x is coming out to be something like 0.394 10 to the power minus 3. Okay, and here it is coming out to be something like 4.2 into 10 to the power minus 4. So here there is a difference in the sign because the assumptions which are there in SAP and assumption which you are doing, that may change. Okay, but if you see overall, so this is if you do this calculation, so you should get over here, it is 3.9 10 to the power minus 4, and here you are getting 4.2 10 to the power minus 4. So this is also very close one. So this is minus value and this is plus value. So definitely the other value is also the sign for other value rotation is also changed. So if you see the other value, it is 0.5 10 to the power minus 3, it is positive. So here it is negative and it is coming out to be 5.3 10 to the power minus 4. So in general, if you see the sign, so signs are basically exactly reverse because of the assumptions, difference in assumptions. Otherwise, the values are concerned, they are fairly matching with each other. Okay. Now, if you see the bending moment diagram, so here this is the bending moment diagram for member 1 or the values which you have calculated. So for member 1, the bending moment at node 1 you have calculated as minus 3.1, and at node 2 the bending moment value was calculated as 46.89. Okay, so let me draw the bending moment diagram also. So let me slightly zoom out so that you can see the values. Okay, so I'm going to F say values. Okay, So this is your member number 1. So member number 1 is having 47.63. Okay. So and what we have got 46.89. So it is a very close. Okay. And the second value is 3.11. And if you see over here, it is coming out to be 3.56. Okay. So this is also very close. So 3.56 and 3.11. Okay. If you go for the second member, so the second member is 3.34. Whereas here it is coming out to be 2.56. So again, this is quite close. The other end, you have 61.97, whereas in your manual calculation it is 61.42. So here you can see both the values, they are exactly, not exactly, but fairly matching with each other. So we can say, yes, this results what we have calculated, they are correct. Okay. So I hope you have understood this. Any questions? Please let me know. Yes, boys, girls. Any questions, please?
No, sir.
Okay, so let me stop the recording. And now